after mid-sim of CH425 and CH812. Can you hear me clearly?
Yes, sir. Crystal clear.
Yes, sir.
Good. Yeah, so we'll wait for a few minutes. Let people come. So,
Good morning, sir.
good morning, good morning. So, so far, whatever been taught, I hope you have gone through the class notes. And there is a book by Griffiths, Introduction to Quantum Mechanics. Please go through the book. This is a book. How many of you seen this book? This is the Introduction to Quantum Mechanics by David J. Griffiths. It's very, very useful book. Okay? So actually you can go through. It will be quite useful. Actually, you should always read from books to get the language and get the feel for the subject. It's always good to go through a very nice book. This is a nice book, Griffiths. So in the last class we did this harmonic oscillator, no? We'll start from there. So let me start sharing. Can you see the slides?
Yes.
Okay.
Yes, sir.
Yeah. What is more important for this course? This part, spin is not spinning on its axis. Spin of an electron is not some object, a tiny ball spinning on its axis. You should get this thing clear. Okay? That is very important. We'll come back to spin today, later. So then I'll just recap all these things. So we'll start with harmonic oscillator. Okay? So wait for a minute, we'll start. Okay. So let us begin. We are doing one-dimensional harmonic oscillator. Remember, this is the potential. This is a Hamiltonian operator. And we had defined two operators, A plus and A minus. It is defined as follows. It is a linear combination of X and P in a particular fashion. See, X and P are Hermitian operators, but these are not Hermitian operators, but these are non-Hermitian operators, but these are called raising and lowering operator. I showed you because you can express this, the Hamiltonian in terms of these operators. The operators, how they appear, the order in which they are appearing, A plus, A minus, or A minus, A plus, that matters because they don't commute. Okay? And I told you, and actually I showed you that A plus is the raising operator. Remember? Because if I calculate this quantity, that Hamiltonian operator operating on a wave function which I'm calling psi nu, which is generated because of the operation of A plus on some state psi. Then I had shown that it is equal to something like E plus H cross omega and then this a plus psi back. So essentially, this psi nu is an function of H, but with eigenvalue not E, but E plus H cross omega. Is this clear to all of you? This is very important. This should be clear. So this new wave function I had shown in the last class is given by A plus operating on some wave function psi, for which the eigenfunction value is E. Are you guys there? Because I cannot
Yes, sir.
see you.
It's clear,
When
sir.
I project, I cannot see you. That's the problem. So these wave function, now if I operate Hamiltonian on this wave function, I get eigenvalue E plus H cross omega. So the effect of this A dagger is to transform the wave function to a new wave function which has eigenvalue E plus H cross omega. So it raises the state. That's why it is called raising operator. Hope this is clear to all of you. So
Yes, sir.
if you want to know more about it, please read the book by Griffiths. Okay. Now also we did, yes.
Sir, in the operator A plus and A minus that we have defined here,
Yes.
sir, it is basically the factorization of the Hamiltonian, right, sir? Because the Hamiltonian, sir, that we are using here.
Hamiltonian is this.
Yeah.
This is Hamiltonian.
Yes, sir. So I think if we take the product of this A plus and A minus, that basically gives us the Hamiltonian, right, sir?
Not really. You have to multiply with H cross omega and then add last half. That gives you. So A plus and A minus is something known as number operator. It's like N, because you know that your Hamiltonian operates on E. Psi will give you. You know that from your harmonic oscillator. It is N plus half H nu, isn't it?
Yes.
So
Sir.
A plus A minus is something known as the number operator. Okay. This is N. This is N. When it operates on psi, it gives you N. This is fine, no? Yeah, we'll see. So I said that actually you cannot go below psi 0. So if you operate A minus on psi 0, it will be 0. Okay. And of course, obviously I did not show, but you can show, like for the A plus operator, for A minus operator, it lowers the wave function. So it is called lowering operator. So that's why if you operate on already the ground state, there is nowhere to go. So this operation gives you a null vector, a null state, 0. And we had used this to calculate psi 0. You remember this thing? I think this is where we had stopped in the last class.
Yes, sir.
Yes, so this is psi 0, and then we had used this Gaussian integral. This is the standard integral, and we got some constant times exponential of minus x square kind of behavior. And this is nothing but the ground state of your harmonic oscillator. Okay, so we'll start from here today. Any question so far? I don't think there is any question. Please go through your slides and read the book by Griffiths. Very important that in my course, it's very important you read books, and good books. I'll tell you as we progress. I'll tell you the names of the books. For example, there's a nice book by Shankar on quantum mechanics. Maybe some of you had seen that book. People from BS, they should know the name of the book, Shankar. Some of you.
Yes, sir.
Okay. So let us start here. So what I'm going to do, so this is what we had. So can I copy this? I don't know. Yes, should we? Just thinking I should be able to copy, or otherwise I'll write. Yeah. It is easier to write for me. Anyway, I'll write. There is a function. Let us take this. So your psi naught is, okay, one thing. I don't expect you to remember all these things, this coefficients. It is not expected. So I am not going to ask any question that you have to remember this. But what you should know, this is Gaussian, the ground state. I think many of you know this. The ground state is Gaussian. Yes. Okay, so this is the ground state. How does it look like? How many of you know?
Bell-shaped curve.
Yeah, it is a very simple thing. It's a bell-shaped curve. If you plot like this is the harmonic oscillator. This is your v equal to n equal to 0. Then it would look something like this. This is it. This is sine 0. Okay. So now let us do something else. It is obvious that if I keep on operating, okay, let us do it later. So let us try to do this. Say you get psi 1, and of course you get psi 1 from where? From psi 0. What should I operate on psi 0? A plus. And then I put some normalization constant here, A1. Is this clear? If I write like this, is it fine? This is normalization constant. If you have any question, tell me. This is very simple. I operate A plus, raising operator on psi 0. What I should get? I should get psi 1. But of course, I have to multiply this some normalization constant in order to get normalized psi 1. Okay? Is this clear? So let us do it.
Yes.
Do it explicitly. So A1. What is the definition of A plus? If you see my notes, you see the definition is like this. The prefactor was this. And then what was inside? Remember? Minus IP. I think that was the, this is exactly, this was the operator, isn't it? If I do something, any mistake with the sign, let me know. I think that is how it is.
M omega x.
This is fine, no? Someone has some noisy background, but this is fine. Just tell me if it is fine. Somebody has to tell me.
Yes, sir.
That
Fine.
I'm,
Yes, sir. Yes,
yes.
sir. Fine.
Yes, sir, it is.
Good. So this is A1. Now what is I, like what is P, you know? I'm just doing it. I square is -1. So it will give you minus H cross . It's fine. So let us go to the next slide because I don't have space. So what I had here was A1 times I think minus H cross del x plus m omega x operating on psi 0. This is exactly what I had, no? What is psi 0? I just substitute the value of psi 0 here. Let us do it. A1. Okay, the psi 0 has a constant thing, so I can just put it here. The constant was like m omega pi h cross 1/4. Can you see the slide, or maybe I'll make it slightly bigger? That helps. This is fine?
Yes, sir.
Yes,
Yes,
sir.
yes, good.
Yes, sir.
Yes. This one plus m omega x. Sometimes I forget to put the cap. But better to put the cap. And what is this psi 0? This is, I think, psi 0. Okay. So what I'm going to get now, if I do it, so this one will give you ddx of this is, you know that, no? What should be?
Minus h plus 2x e to the minus m omega x square by 2h plus.
Plus I think this is fine. Should be fine so far. Let me know if it is fine. Hopefully, I think it is fine. So if I simplify it further, what I'm going to get plus minus is plus, h cross will cancel, isn't it? This will give me what? 2 will cancel. This will give me what? M omega x.
X e to the minus m omega x square.
This also has what? M omega x.
So twice of m omega.
Yeah. Okay. Now, how can you calculate A1?
Sir,
Yes.
so I think you missed out on a
Normalization.
term extra from the last step.
What term?
1 by under root mh cross omega. I mean 2 mh cross omega.
Yeah, you're right. Okay, I'll put it there. Here. Yes, you're saying this one. This factor is there everywhere. Okay. Yeah, so let us see. Sorry. Twice h cross m omega, and this, you have this, and you can, this will be like twice m omega. You have the x thing, of course, but then you have m omega pi h cross whole to the power 1/4 into a1 into x. This is exactly what you have, and this will give you what? So m omega will cancel partially, no? Okay, we'll do it later. So let us calculate a1. Okay, so I can do it here. So actually this will give you root over twice m omega. This is fine, by h cross into m omega by pi h cross 1/4 a1 x e to the power of minus m omega x square by twice h cross. Okay, this is fine. Now to find a1, can anyone suggest me how to find a1?
Normalization.
Yeah, so normalization. So a1 you have to find like this. So you have to take whatever I assume this is, of course, this is real function. So this is has to be equal to 1, which basically means a1 square into actually you have to make a square of it. If you make square of it, you're going to get and then you have integral. What is the integral? This is the integral. Okay.
Yes, sir. Standard.
It won't be the 2 in middle.
Should be 2 should
be
not
what?
be there, I guess.
Yeah, no 2. You're right.
And it should be m omega by pi
No,
h plus 2 and
no,
half.
no. There will be 2 because this.
Yes, sir. 2 will be there.
Because root over 2 and 2, no? Root over 2 is there. Root over 2. If I cancel these 2, Anish, this root over 2 will there, and if I make a square of it, it will be there will be 2, isn't it?
No, I'm saying
I think second term.
Exponential
Yeah.
term.
Okay.
1 by 4.
I understand. So, yeah, that's a typo. This is what you're saying, no? Yeah.
that is okay, but if you take that constant term m omega by pi h plus power 1/4.
Yes, that is one half. Yeah. So this is how it is, isn't it? So now you have to do the integral, this integral. So this integral, let us do it here. How many of you know how to use, what is the value of this integral? Anyone knows? Let me write it down.
Sir,
If you have
isn't it a standard integral or we can
Yes.
solve it?
Yeah, of course. This integral is given by
Gamma function, I think.
okay. So we'll just
x की power and e की power minus alpha
okay.
formula.
The formula I have written here. Can you see the formula? So I don't expect you to remember the integral value, and I'll show you how to calculate this integral. So say let us call this integral I. I is this. And now I take a derivative of I with respect to alpha. The alpha is sitting there, no? What I'm going to get? Tell me. What I'm going to get? Please tell me.
Get minus alpha.
Minus. Minus.
So I'm going to get, sorry, not this, sorry, I've done it wrong.
We should differentiate.
Yeah, this one. I'm differentiating this one, okay? Only this standard integral, which I know very well. So if I differentiate, I'm going to get minus, you can see, minus x square, because you are differentiating with respect to alpha, into, this is fine if I write like this.
Yes, sir.
If I write like this, okay, and say let us call this integral j. So what I have here is essentially minus j. Is it clear? Is it clear to all of you?
Yes, sir. Yes, sir.
So j is actually minus di d alpha. And I know this this is standard integral. This is pi by alpha to the power half. So then what is di d alpha? Minus di d alpha, pi to the power half. You remember, no, this? N x to the power n, no? Is this clear? I have a minus sign here.
It should be minus 3 by 2.
So it is going to be, actually, if you write carefully, it is exactly like this, whatever I've written here. I can rearrange. It is going to be like this because you have alpha to the power 3 by 2, you have, no? minus 3 by 2, and then this half, and then pi to the power half. Okay, and this minus minus will combine. So this is the integral j. This is the value. I have written this, and I have proved starting from the standard integral. Is this clear to all of you?
Yes.
Look at
Yes,
it.
sir.
It is not
Yes,
very
sir.
difficult. So what is alpha in this case? Here, alpha is what?
M
Zero?
omega by
Omega
h
by
cross.
2.
Minus
So
m
then,
omega.
so then this integral is going to be what? 1 by twice alpha means 2h cross m omega into you know that pi by alpha. Pi by alpha means pi h cross by m omega whole to the power of half. What is going to happen? What is going to happen? Can you see what is happening here? Is this clear to all of you? And then you have this factor. I hope I have done everything correct. Maybe I have done some mistake here. I think I have done some mistake. It should be the other way, isn't it?
Yes, you have written
This
the 1 by
factor.
2 alpha term.
Yeah, so 1 by 2 alpha is going to be the inverse of this, isn't it? Not exactly, actually inverse of this, whatever is there.
H cross by 2 m omega.
Yeah. So this one is going to be h cross by 2m omega. So what? So basically this is quite nice, no? Why it is nice?
So A1 is unity.
Yeah. So the way it is done, so A1 is unity. So you can cross everything. A1 is 1. And now I know the solution. So basically I know that psi1 is going to be this one. So you can just multiply this thing, I don't care. So it's essentially it is and you can go back and check any book, you'll see that this is the expression for the fast excited state, or n equal to 1 level of simple harmonic oscillator. You remember this, no? If you have harmonic oscillator like this is 0, this is 1, 0 is like this, and this is going to be like this. This is hand drawn, so not perfect. Is fine? Is it
Sir,
clear to all of you? Yes, tell me.
sir, I am having a little confusion in differentiation of I. Like, I have not the mathematical background. Like, how can we differentiate an integral like
Yeah,
that?
you're differentiating integral because this is a function of alpha as well as x. And as far as the x is concerned, it is independent of alpha. So when you differentiate this with respect to alpha, so only
So is this
alpha,
partial differentiation?
you can call it as partial. Actually the differentiation and integral, they commute. So if I differentiate this with respect to alpha, so what is x would be anything of x would be constant to this, isn't it? You remember that if I have an integral like, okay, I'll show you. If I have an integral like this, exponential of say minus x square, and if you do ddx, what do? Say alpha x square. What will the answer?
Minus 2 alpha e raised to power minus x alpha x square.
It is going to be this, isn't it? Isn't
Sir,
it?
alpha will also be out. Like, we are differentiating with respect to x. Alpha should be there also.
Yes. So this is the answer, isn't it?
Yes, sir. Yes, sir.
This is the answer. So, but
Yes,
here you are doing the other way. Then what will be the answer? Tell me. You understand exactly this way.
minus x square e raised to power minus alpha x square.
So exactly this is what I did here, isn't
Okay,
it?
so you're saying that it doesn't matter if first we integrate then we differentiate, or first we differentiate then we integrate, like
Yeah,
they
yeah,
are
they
commuting?
commute. They commute. Of course, they commute. Yes, definitely.
Yeah, the dx will remain as it is. So
Yes, yes, yes. So this is how it is. So actually, this is very useful, because if I have an integral like this, x to the power of n e to the power of alpha x square dx, what will the answer? N is integer. Can anyone tell me what is the answer?
So 1 upon n alpha.
Something will be there. I am not going to write down that. But this is 0 if n is odd. Is this clear?
This is an odd function, right, sir?
And if it is non-zero if n is even. So all the even moments, like anything where n is even integer, are non-zero, and you can calculate that. So if I ask you to calculate this integral, you should be able to do it, no?
Then the integral will be integration 0 to infinity, 2 into 0 to infinity
No,
in the
no, no.
function.
You can do that, but how do you are going to do it? How you are going to do it? You are going to do it because you know the integral this. This one you know. What is the answer? This is the answer. Okay, then just call it k. Then what is dk d alpha? This is nothing but minus of, if I call it say k tilde, sorry. If I call it k tilde, this integral. So this is nothing but minus of k tilde. Is this clear? Because if I differentiate this with respect to alpha, what I'm going to get? Another x square will come down here with a minus sign. So this will give you minus x to the power of 4. Sorry for minus x to the power of 4 e to the power of minus alpha x square dx. Okay, and this is your minus of k tilde. So basically, you have to differentiate this with respect to alpha and multiply it with minus 1. That will give me x to the power 4 into that integral. So you can do all the even moments like this. Is it clear to you? It's very simple. And odd moments, like when n is odd, they are 0. You don't need to do the integral because the whole function is odd function. Anyone having a problem? This is very simple. If anyone has a problem, let me know. Anyone has a problem, let me know. Okay? So we'll start a new topic here. Since nobody has said anything, I'll start a new topic here. Okay, before we start, this is obvious that your En is going to be n plus half h cross omega. If you operate on n times, basically your psi n is something like a plus operating n times on psi 0. These two things you can check, and this is going to be okay. So now let us go back to your operators. This one you know, remember Lx, Ly. These operators you remember. It is done with I think in the last class briefly I mentioned, maybe in the first class I think. And I think everybody now know what is this. What are these operators? What are these operators? Anyone can tell me?
Angular
angular
momentum.
momentum.
X component and Y component. Okay.
Yes.
Now I'm doing a new topic where I'm constructing some operator, say L plus, which is Lx, plus ILY, like similar to what I did for harmonic oscillator A plus, which was something like combination of P and X. Here is combination of LX and LY, and L minus as LX minus ILY. Fine. So I'm lazy. Sometimes I'll not put the cap. Huh? Don't mind. I'll try to put, but sometimes I may forget to put the cap. But these are operators. Is this clear? Okay. Now
Yes.
if I ask you to calculate this L square commutator with commutator with L plus minus 1. Plus minus, you understand what I mean. If I write L plus minus 1, because this is shorthand notation. This notation, you know, everybody knows this. So it could be plus, could be minus. So I'm writing two equations together. What is this going to be? This is going to be L square, sorry, L plus minus minus L plus minus L square. What is the answer? Can anyone tell me?
0.
Just without doing the math. It is 0. It is going to be 0 because L square commutes with LX, LY, and so it is going to be 0. Because you can do this explicitly and you check, but it's going to be 0. Okay. So, but now let us do this commutator rather, sorry. LZ L plus minus 1. So I am doing it together. It basically means I'm doing two commutator. One is with L plus, one is with N minus. So what is the answer? The answer is like as follows. If I write like this, is LZ, comma, LX, and then plus minus I can take common, LZ, LY. Is this clear to all of you? I think it is clear because I'm using the definition of L plus and L minus.
Yes, sir.
When I consider L plus, this is plus. When I consider L minus, this is minus. Huh? Now you remember what is this commutator? This commutator, you remember, no? LZ, LX, we have done it. Can anyone tell me what is LZ, LX?
IH cross LY.
IH cross
IH cross LY. And what about this guy? LZ, LY?
Minus IH cross LX.
Minus
so
I.
IH cross LX. So this is going to be what? So I square is minus 1 and this minus will combine. It will give you plus 1. Okay. So this one I can write it as like this. So I'm just going to write it like this. See this. So I'm not combining this minus and this minus. So let us write it down. Let me tell you. IH cross LY. Let it be here plus minus be here. What I'm going to get? Then I'm going to get minus. Sorry. Yeah. So if I combine this with this, it is I square is this is 1, no? This is fine if I write like this. This is fine.
Yes, sir.
And now remember, now this one I'm going to write like this. So the next step I'm going to do something like this. I am going to take this plus minus H cross common. If I take plus minus H cross common, what I'm going to get? I'm going to get LX from here. What I'm going to get from here, can anyone tell me? If I take plus minus IH cross common. If I take plus minus IH cross common, I'm going to get a
Minus
plus.
plus.
Minus plus ILY.
No. This one. I'm going to get plus minus, no?
Plus minus ILY.
Yes. And what is then what is this plus minus H cross? What is this? LX plus minus ILY. Tell me what is that?
L plus minus.
L plus minus. This is fine. Is this fine?
Yes.
So this is very interesting thing. Very important thing. So what I'm going to use. So let me write down the result here. The commutator of LZ with L plus minus is equal to, what is the answer? plus minus H cross L plus minus. This is fine? This is what I did no right now. Okay, now let F is an eigen function of say L square and Lz. Okay. So now it's such a way that okay, when I operate Lz on F, it gives me something like say mu times F. Okay. So now let us calculate this quantity. And okay, and when L square operates on F, this notation is a problem. So lambda F. So now let us calculate this quantity L square L plus minus F. It is going to be what? Can I write it like this? L plus minus into L square F. Can I write like this?
Yes, sir.
Because
Commuted as it.
why? Because they commute. Because L square and L plus minus commute as. So what is the value of L square operating on F? This gives you lambda F. This is lambda F. Okay. So then you can take the lambda out because it's a constant. Okay. This is fine. This is clear. So basically,
Yes, sir.
what it tells you that even L square when operates on this wave function L plus minus F gives you lambda times L plus minus F. So in other words, L plus minus operating on F. This is a new wave function. No, is an eigenfunction of L square with eigenvalue. What is eigenvalue? Lambda. Is it clear? Is it clear to all of you?
Sir, can you please explain this?
Very, because this when lambda L plus minus F, it gives you something like what? Some F nu. And I have showed you that L square when operates on F nu, what I am going to get? I am going to get lambda times F nu. This is F nu, no? This is F nu.
Okay, okay, sir.
This is I am writing in using a language and side, writing it like this. Okay. So now let us calculate this. Lz operating on L plus minus F. Not L square, now Lz. So let us write it like this. So let us like this, like Lz L plus minus. I am subtracting something. I can subtract, no? And then I have to add that. It's fine because I'm subtracting this and adding this. Nothing else. Okay? Is this clear to all of you? Now,
Yes, sir.
what is this quantity? Can anyone tell me? This quantity.
Commutator.
Yes, yes. Commutator of Lz with L plus minus. So this is given by this expression. So what I'm going to get here?
Plus minus X.
Yes. Some noise is coming. Please mute yourself. I don't know. Please mute yourself. Yes. So this one is going to be plus minus H cross H cross
L plus minus.
L plus minus on F. That is what you have, isn't it? And then plus what you have? Now this one, you know the answer.
L plus minus mu f.
Yeah, because this is L plus minus, and I know this one is, I have written somewhere, mu f, no? So this is like mu f. Is this clear? So this one I can actually again write like this, mu plus minus h cross L plus minus f. This is fine. If I write like this, is this clear to all of you? Should be clear. There's not much I did. Is this clear to all of you? Because this is your mu and h cross. They are constant. So what does it mean? What does it show you? What does it tell you? Can anyone tell me? Basically, it tells you, let us take a
This
different
is
color.
also an eigenvalue.
Yes.
Yes, sir. But the eigenvalue is different.
So this I call something like, say, f prime. So f prime is an eigenfunction of Lz, but with eigenvalue. What is eigenvalue? Tell me.
Mu plus minus h.
Mu plus minus h.
So of course. So then basically, I mean, if it is L plus, then the eigenvalue is mu plus h cross. If it is L minus, then the eigenvalue is mu minus h cross, isn't it? That's why it is plus minus, no? So basically, it tells you what? What is L plus then? You should call it what? You should call it raising operator. Of course, this is in terms of angular momentum operator. And this is okay.
Sir,
Yes.
sir, I'm not able to understand the physical significance of this.
Okay.
Like, what are we raising here? Can you?
Yeah. So the raising, we just said the raising, we're raising the state like here. You start from here. If you operate, in this case, it was A plus. If you operate A plus, you raise from state 0 to state 1. That's why it's raising. And if you operate A minus, you go you lower from state 1 to state 0. That's why it's called raising and lowering operator. It is going from one state to the other state.
Sir,
Yes.
so here we are like raising angular momentum. So if we have a function, if we apply L plus on it, it will give us a function with angular momentum something h plus h cross, right?
Yes. You're right.
Yeah. So it will raise the angular momentum.
Yes. The value it will be 1 unit higher. I'm going to do that now.
So like it's for like simple harmonic oscillator. Like so we have fixed state.
No, this is not simple harmonic oscillator. This is your angle hydrogen atom problem I'm doing now, isn't it? We did the simple harmonic oscillator just few minutes back. A plus and A minus. This is L plus and L minus. These are angular momentum.
Okay, sir.
I told you, no. I'm starting a new topic. I told you, no, I'm starting a new topic here.
So
okay.
I think, yeah, clear, sir.
That's why I have different notation, L plus, not A plus. So what is going to happen eventually? You can keep on rising, but can you keep on rising forever for in this case? No, because the Z component of angular momentum cannot exceed the total angular momentum, isn't it? You know that the
Yes,
Z component cannot exceed the total angular momentum. So eventually you will reach a state for which the Z component exceeds the total. Okay. So basically I can write eventually a state for which above which actually z component of angular momentum, of course. Exceeds the total, but it cannot happen, no? So there is a top, I will call it rung, following the book of this Griffith. So what does it mean? Can anyone tell me mathematically what does it mean? You should be able to tell me. Mathematically, what does it mean?
MH cross cannot be greater than L into L plus 1.
No, not like that. Mathematically means that if I operate L plus on some state like ft means f top, okay, then what is the answer?
0.
Is 0. This is exactly what is meant by this statement. You cannot go beyond that, because if you go beyond that, you are going to break this thing. Your z component is going to be more than the total. That cannot be. Okay, and let H cross into L is the eigenvalue of Lz at this top rung or top state, whatever. Okay, what does it mean? If I operate Lz on this ft, t for top, what is the answer? It is H cross L times ft. Okay, so I am operating this operator on this, and I am getting some eigenvalue H cross L times ft back. But remember, if I operate L square on this, what I am going to get? Something like, sorry, on ft, what I am going to get? Something like lambda times ft. Okay, so let us do it. Do some little bit of algebra. We are almost done. In 10 minutes, we'll be done. Don't worry. Yes, tell me.
Sir, can you please explain the zero part, like why it is zero? It can also be not defined, like what does
So this is how
that
it is
make
done
an-
in quantum mechanics, because it basically means that you go to a null state. So that state does not exist. So the state for which the state is null state, basically because the vector associated with that state has a zero length. So basically it tells you, takes you nowhere. So exactly the similar statement we gave when harmonic oscillator, remember, you go to the zero state. If you want to go further down, you cannot go. So if you operate a minus on zero state, you get 0. Similarly here, if you operate L plus on this top state, you get 0. There is nowhere to go. It will be 0.
Sir, it means that it will not raise the function.
It will not. It cannot reach the function. Yes, because there is nowhere to go, because it will then break this.
Sir, after certain state,
After
we will
certain
get zero value,
yeah,
na?
for a given value of the total angular momentum, there is always the upper state, the topmost state for Lz possible, because it cannot exceed. You remember that L, say for the L1, there are 3 possible values, isn't it? -1, 0, and 1. Okay, so you cannot exceed that. You cannot have m value, say 2 for L equal to 1. That's why, so if you want to, for a given value of the total angular momentum, the state, there is a top state. If you operate the raising operator on the top state, you get 0. You get a null vector. There is nowhere to go. So this is very important. So let us do this. L plus minus into L minus plus. You understand what I'm written here? What is that? It is Lx plus minus ILy into what? Can anyone tell me? Lx
Minus plus.
is
Minus
minus
plus.
plus ILy, sorry. Okay? This is how it is. Can you expand this? Tell me what are the terms I'm going to get. I'm going to get Lx square for sure. I'm going to get Lx square for sure. Okay. So then
minus plus I Lx Ly.
no, let me do it the simpler thing first. Lx square. Okay, now if I multiply this with this, what I'm going to get? Ly square, obviously. I square will give me -1, but this plus and minus will give me another minus. So it is always plus, isn't it? Because here
Yes.
also you have minus and plus. So this will give you plus Ly square. Okay. Now you tell me the other terms. Yeah, somebody was telling me.
Yeah, I plus minus I Lx Ly.
Is it plus minus?
Sorry, minus plus. Sir. So
Yeah,
minus.
that is very important. So let us do it this one. This guy multiplied with this. What I'm going to get? I'm going to get minus plus I Lx Ly. What about this guy multiplied with this? I'm going to get, tell me, I'm going to get plus minus I Ly times Lx. Is this clear to all of you?
Sir, please, sir, please, once more the Ly square term. Please say it again.
Ly square
How
term
is-
is very simple. This Ly into Li is Li square. I into I is -1. You know that I into I is -1. I square is
Yes, sir.
-1.
Yes,
And then this plus into minus is what?
Yes,
-1.
minus,
-1.
yes,
Minus
sir.
1 into
Okay,
minus
okay.
1 into +1.
Okay,
On
sir,
the
fine.
other hand, this minus into plus is also -1.
Also minus and yes.
In
sir,
all
fine.
the cases, it is +1. So that's why it is plus, always plus. Okay. And now
Yes, sir.
again what I'm going to do, I'm going to now take this common, minus plus I. If I take minus plus I common, what I'm going to get inside? I have taken minus plus common. I is okay. This is going to change the sign, isn't it? This is going to change the sign, plus minus.
Yes, sir.
Okay. And what is that?
IH cross LZ.
This is a commutator, and I have done this earlier. This is Lx Ly, and this is IH cross Lz. So I'm going to use that here. So what I'm going to go, so Lx square plus Ly square, can I write it like this? L square minus Lz square? I can write, because your L square is, you know this.
Yes, sir.
Okay, so sometimes I just change this cap and square. Anyway, so this is how it is, and then this one is going to be, tell me, minus plus I into IH cross LZ. Then what will be the next step?
L square minus LZ square plus
I am
minus.
doing it very carefully, because I and I will give me what? -1.
Yes.
-1.
And this -1 and minus plus minus, this will change the order, isn't
Plus
it?
minus.
Is fine? Is fine? So this also tells you, because this is what? This is L plus minus L minus plus. This also tells you L plus minus L minus plus is equal to this. So let me write it down one more time. Okay, so this implies that I can express L square. L square is going to be what? L plus minus L minus plus. L square I take it on the other side, no? These two I take it on the other side, plus Lz square. What is going to happen to this guy? Tell me.
Minus plus.
Minus plus H cross Lz. This is clear? What I've done here so far?
Yes, sir. Fine.
So this is going to be again useful, very useful. We'll see in a
Sir,
moment. Yes.
can you explain the second line.
Which
like,
one? Tell me this line.
Sir,
This line.
right side second line.
This one. Which one? Tell me.
Sir,
I'm
cursor
showing.
is-
Yeah, I'm showing my cursor. No, you should be able to see.
Yes, sir. This one. Yeah.
Yeah, I told you. No, this one is Ly square. You know how to get it, because Ly into Ly is Ly square. Because I square will give you -1, and then plus into minus will give you always -1. -1 into -1 is plus. That's why it is Ly square. And then it is like this. This one is Ly Lx with plus minus, and the other one is Lx Ly with minus plus. Minus plus Lx Ly. If you do carefully, this is how it is going to come. Do yourself.
Okay, sir.
Okay. So now I have expressed L square in terms of L plus minus L minus plus Lz square, L squared there, and then minus plus H cross Lz. Okay. Is this clear to all of you? So now I am going to do this. So what I have here, let me write it one more time. L square is L plus minus L minus plus Lz square minus plus H cross Lz. Okay. So now I operate L square on this Ft using this expression. Okay. So I take the first one. I take the second one, L minus L plus, this thing. L minus L plus. What will be the next term? Tell me. Plus Lz square. What will be this term? Tell me. I'm taking minus plus. Then I should take the lower one, no?
So
Plus.
plus.
And this one operates on the Ft. Ft, T for top, the top one. What I'm going to get now? What is the first term? This one operating on Ft?
0.
0, because L plus operates on Ft gives you 0. So 0. The next term is Lz square operating on Ft. Essentially Lz operating twice. What should be the answer?
L square.
H cross square L square into Ft. Let me write down it. And next one is H cross is there, but again you will get H L Ft. So this will give you something which is familiar to you.
L plus 1.
The structure looks similar, familiar to you. So basically your lambda is, because I had told you that if I L square operating on Ft gives you lambda into Ft. So the eigenvalue is H cross square into L into L minus L into L plus 1. Is this clear? Okay. Now similarly, if I operate L minus on something like FB, B for the lowest possible value, base B, call it. This is what going to be 0,
0.
because you cannot go down further. If you cannot go down further, then again I write this L square operating on FB, and this time I take the other definition. I take this definition, L plus L minus plus Lz square. What will be the next term? I take this plus minus, so it should be minus of
H cross Lz.
H cross Lz. And if I operate on FB, what I'm going to get? Why did I take this particular combination? Because I want to operate L minus on FB. That's why I take L plus L minus combination, not the L minus L plus combination. So the first term is 0. What is the next term? Tell me. Now in this case, let me tell you one more thing I did not tell you. In this case, for the lower thing, the Lz operating on FB gives you H cross times some L bar times FB. So what is going to get here? You're going to get L bar square H cross square into FB, and the next term is going to be minus H cross square L bar FB. So if I just write like this, it is going to be, sorry, L bar minus 1 into FB. Basically, it tells you again the lambda is L bar into L bar
Sir?
minus 1 H cross square. Yes, tell me.
Sir, the operator LZ square when operated on FT. Sir, I'm not getting. You have written H cut square LFT.
Yes, very simple, no? If you operate LZ square operating on
Sir, it gives
FB,
sir angular momentum operator, na? I mean eigenvalue when
yeah.
LZ square.
So what is that? I told you this is H cross L into FB. So this will be H cross. If you operate twice, what you got to get? H cross L square of that, no, into FB. That is what it is, no? H cross square L square. This is exactly what I have written here. What is your problem?
Sir, I mean to say, so when LZ operated on any function, it gives eigenvalue of LZ.
Yeah.
Under
So
root LL plus
we'll
one.
see.
That's
We'll see what is that. So forget, for the time being, you forget that you know what are the eigenvalues of LZ. Okay, I have not told what is the L bar. Huh? So now I compare this equation 1 and 2. Okay, so if I compare this, what gives you that? One possibility is L bar is equal to L plus 1. One possibility. Because what I am comparing this, I'm saying this is equal to H cross will cancel. So this is how. So one possibility is this. Is this acceptable? Can anyone tell me? Is this acceptable?
So if L bar equal to L plus 1, then the bottom rung of the ladder is above the top rung.
Yes. Absurd. Because the bottom rung is above the top rung then. Because your L bar cannot be more than L, isn't it? So what is the another possibility?
L bar equal to minus L.
Yeah, because if I put L bar equal to minus L, that will also minus L into minus L minus 1, minus will combine, give you plus. So it will be L into L plus 1. So another possibility is, and this is acceptable actually, which basically tells you that your lambda is this. Okay, lambda is this. Okay, and not only that, if I assume that L behave like 0, 1, 2, 3 like this, then this L, I had this eigenvalue, no, L into H cross. This will be interpreted as M into H cross. These are the Z component of your total angular momentum. So in other words, I can write that when L plus, sorry, not L plus, sorry, on L's, when L square operates on this L square, when it operates on say F, which is L and M, and given by L and M, I'm going to get L into L plus 1 H cross S square into F L M. Similarly, when I operate LZ on F L into M, I'm calling it M H cross F L into M. Okay, so these are things you know. Okay, these are things you know. Now what is important here, I'm going to write something which I'm not going to prove. It is going to be an assignment problem. that if you operate L plus on FLM, what I'm going to get? I'm going to get FL
M plus
M
minus 1.
plus minus 1, but there will be a coefficient here, AL M. This will depend on L and M. Okay. One can show, and this will be an assignment problem, that this coefficient ALM is given by, how many of you know? I don't know, H cross. Maybe people who have taken physics code, they would know. L into L plus 1 minus M into M plus minus 1. Okay. One can show like this. So this is going to be an assignment problem. We are not going to deal with this right now. Is this clear? Okay. So this is all about your raising and lowering operator for the angular momentum. But we'll now come back to spin and just mention
Sir?
few things about spin and finish. Yeah, tell me.
So can you repeat this, sir? L caps acceptable that we have written in the previous slide.
Yes, I'll do. See, if I compare these two, L into L plus 1 equal to L minus L bar into L bar minus 1. One possibility is that L bar equal to L plus 1. If I put that, that will match, no? Because L bar minus 1 will become L bar and L bar will become L bar. L bar minus 1 will become L bar will become L plus 1, isn't it? This will match.
Yes, sir.
But this is not acceptable. Why? Because it tells you the L bar, which is for the lower rung or the lower state, is greater than the higher state. It cannot be, no? It cannot be. L bar cannot be greater than L. So that is not acceptable. So other possibility is that L bar is minus L. And that is acceptable. And if I accept that, your lambda is going to be L into L plus 1, isn't it? Into H cross square.
Yes, sir.
That is eigenvalue. This is exactly what I said, nothing else. Now you come back to spin. We had started doing spin, no? So let us come back to spin, and I had told you that like orbital angular momentum, similar commutation relation will hold. So if I write Sx Sy, what will be the answer?
IH cross SZ.
IH cut SZ.
Okay, so and I of course I can write like Sy Sz. And Sz Sx. So all the similar relations. Okay. Now I can write S square operating on. Are you okay with this notation? Sm. I did that in the last class, but you have not used this notation. We had used this notation. What notation I had used? Can anyone tell me what is the notation I used?
Cat.
Last time, in the last class.
So
I
cat
had used
notation.
No, I did not use notation. I think I used like this. If I operate on alpha, it gives you something, and S square operating on beta gives you something in the last class. Now using the Bryan-Kate notation. Okay, now in general, I'm doing it for a general spin, not only for electron. If I do this, what is going to be on the right hand side? Can anyone tell me? I had told you this one, no?
SS plus 1 H cross.
Okay, for electron, what is the value of S? It's half. And what is the value of M? These are plus minus half, isn't it? But you can have situation where S is 1 or S is 2, isn't it? We can have situation. So for example, for photon, we are not going to do this. S is 1. For gravitons, S is 2 of, I think. I'm not going to do it. So here again, you can clearly see that you can have more than two states, and then what you call clockwise, anti-clockwise, then what I'm going to call for photon and other subatomic particles. So it is not physical spin, that is obvious. So this is another notation. So a square operating alpha and beta, I told you it is h square s into s plus 1 into alpha. Similarly, I can use this Kate notation, isn't it? So similarly, if I operate sz on this sm, what I'm going to get? Can anyone tell me? H cross m to sm. Now I'm calling it m. I'm calling it ms also. Okay, if you want. This fine? Is this fine so far? And m varies from ms varies from where? Minus s to plus s as integers, no? So for electron, ms has to be from minus half to plus half, an integer step. So it has to be two states. Is this clear to all of you? Is this clear? Clear? Just tell me. It's very important that it's clear.
Yes, sir.
So if I now operate s plus on this sm, what I'm going to get? Tell me. Because we are making an analogy, we are just mapping this onto the orbital angular momentum. What is this going to be? Can anyone tell me? Can anyone tell me?
Some coefficient into s.
Yes. And the coefficient is going to be this. Look at this expression. This one.
Root s plus 1 minus n plus 1.
Yeah, it is going to be s into s plus 1 minus ms into ms plus minus 1 operating on sm. Is this clear? Okay. This is what it is, isn't it? Now this is not going to be m. What is going to be? Because you are using raising or lowering operator. This is going to be ms
N plus 1.
plus or minus 1 depending on what I operate. If I operate s minus, this will be minus. If I operate s plus, it will be plus. I hope this is clear up to this. So this is one way of showing. This is the Bra and Kate notation. But I can also have matrix notation, no? It's matrix representation. Spin operators. And spin states. And these spin states, they have a name. You know this? They're called spinners. So let us define something. Alpha, beta, you know. So similarly, alpha is equivalent to what? For electron, it is half.
Half plus half.
Half. What is beta?
Half minus half.
Yes, others should also tell. I'm putting it in a bracket. This is fine? But you can also have another representation that your alpha, I'm calling it chi plus, and I'm representing this with a column vector like 1, 0. And your beta, I'm calling it chi minus, I'm representing it with another column vector 0, 1. This is your up spin. This is down spin. So I have like 3 representations, either Bra, Kate, or the simple alpha beta, or chi plus and chi minus as column vectors. These are like column vectors. These are column vectors, okay? Is this clear? So now if I operate this, you should be able to tell me. S square on this chi plus, what I'm going to get? I've already told you this. Other than on it, somebody should tell.
Sir, h cut square half into half plus 1 into chi plus.
This is
H cut square into half plus 1.
into half plus 1. You're right. Then chi plus. This is 3 by 4 h dot square, isn't it? Chi plus. If I operate this on chi minus, what is the answer? What is the answer? Tell me.
Half minus 1.
Same.
Same, sir.
Now, how to represent now? What if I now say a square is given by a matrix like what was the okay C D E F? How can you find these matrix elements? I'm just representing this operator with a matrix 2 cross 2 matrix. How can you find the matrix element?
So multiply this by the chi plus and chi minus and then get the value.
Yeah, very good. So let us do this. A square on chi plus, which basically means C D E F on 1 0. You know how to do the matrix multiplication. You know this arrow. C into 1 is C plus D into 0, 0. E into 1 is E plus F into 0 is 0. This thing into, tell me what is going to happen. This is equal to what? You know that. 3 by 4 h cross a square 1 0. This tells you what? C is what? 3 by
4 h cross square.
E is 0. Now you got C and E. How do you get D and F? Any idea? In that case, you have to operate a square on chi minus, which is C, D, E, F operating on 0, 1. What I'm going to get? I'm going to get C into 0 is 0 plus D, E into 0 is 0 plus F, and the whole thing is equal to 3 by 4 h cross a square 0, 1. And this tells you that D equals to 3 by 4 h cross a square and F is equal to, D equal to 0, sorry. Some problem with okay, almost there. This is where I want to stop today. One more minute. Okay. Don't know what is happening. But obviously, you know that what is going to happen, that your D is 0 and F is 3 by 4 h cross a square. So this will give you the total matrix. The matrix that represents, it's only 1 minute I need. Yes. Okay. I don't know what is happening. Just wait for a minute. Yes. And do it now. Yeah. So this is going to be, which basically tells you your D is 0, F is 3 by 4 h cross a square. Then what is F? C is 3 by 4 H cross S square, E is 0, D is 0, 3 by 4 H cross S square, and I can take 3 by 4 H cross S square common. This is a diagonal matrix 1 0 0 1. So this basically is a matrix representation of your S square operator. I will stop here today. Okay. So the next class is day after tomorrow. Okay. People are there.
Yes, sir.
So next class is day after tomorrow, and what I'm going to do, I'm going to now send you the notes, also upload the videos. So you have seen the videos. There is a folder link shared on Moodle. Videos are there,
Yes, sir.
and another folder in Moodle where you have the class notes. Okay, so we'll stop presenting now. So we'll meet day after tomorrow. I'll send you the link. So thank you very much for joining. Okay, so see you day after tomorrow. Bye.